Previously, we talked about identifying limits by viewing the graph of a function, tracing from the left, tracing from the right, visually understanding what's happening with that function. Now what we want to do is get into evaluating limits just by looking at the function itself, not considering the graph. In example 1, we have one of the simplest limit problems we can consider. We want to find the limit as x approaches 6 of the function 6. And in each of these cases, these first few examples, we're going to use a technique called direct substitution. Meaning what we'll do is take the value that x is approaching and plug that into the equation that we're given, or into the expression that we're given. I said this is a really easy one, but it might look confusing at first because there's nothing to substitute into. If there's nowhere to substitute in, then that value is just 6. Because what's happening here is we're considering the graph of y equals 6, which is just a horizontal line. It doesn't matter what our x value is, our y value will always be 6. So the limit of a constant, which in this case is 6, is always just going to be that constant. Things get a little bit more interesting in example 2 because now we do have a variable in this expression. We want to find the limit as x approaches 5 of negative 2x plus 10. We're still going to use direct substitution, meaning everywhere that x occurs, we're going to plug in this value of 5 and then evaluate that expression, which in this case will give us negative 10 plus 10, or 0. So the limit of that function as x approaches 5 would be 0. Similarly, in example 3, we'll use direct substitution again. Here we're going to plug in x equals negative 3, which would be squared minus 4. Negative 3 times negative 3 will give us positive 9 minus 4, or positive 5 as that limit. In example 4, again, using direct substitution, we'll plug in 0 every time an x occurs in this expression. And then evaluate from there. This will end up being negative 4 times 1, or negative 4. And then we'll do that same process one more time with example 5. Using direct substitution, we'll plug in x equals negative 3 everywhere an x occurs. So we'll get negative 3 squared plus 5 times negative 3 minus 1 all over negative 3 plus 2. This will end up being 9 minus 15 minus 1 all over negative 1, or positive 7. Now we've evaluated 5 limits without looking at the graph of a function. Though at this point things may seem a bit trivial. You've probably been plugging in values for x or evaluating formulas for a given value since at least something like junior high. But these are what I would call the nice cases, the easy cases. In each of these examples, we could use direct substitution because the function was continuous at x equals c. Whatever value x was approaching, that function was defined and continuous at those points. The next few examples we look at are going to get trickier because we're going to consider how we determine the limit at points where the function is undefined, meaning this direct substitution method will fail.